Hello, my name is Jonathan Van Steenberg. My team has been working on a project to develop a more robust adaptive computer user interface for people with disabilities. This presentation provides an overview of the issues faced by people with disabilities, a description of our proposed system solution, details of the system component we addressed in this project, and a demonstration of that component. We have 3 people on our team. Damian Castroviejo is our team leader. In addition, he provided support on database design and programming. Lee Trin is our system analyst and security specialist, and I was the user interface designer and provided programming and testing support. I have some unique qualifications to do the user interface design and testing because I have cerebral palsy, which leaves me with significant motor and speech impairment. I use adaptive software to access my computer and communicate, thus the text-to-speech for this presentation. In this presentation, we will discuss the problem space we are dealing with, and the overall system objectives, as well as our objectives for this project. We will discuss some of the development details and other considerations and will give a demonstration of the virtual keyboard component that we programmed. But first, let's talk about the problem we are addressing. All software users get frustrated with software that makes it hard to get even the simplest task accomplished. There are many people with a wide variety of disabilities that have a need to access computers and other devices. In today's world, computers have become an essential component of day-to-day life. People with disabilities face a true dilemma. They can have a very difficult time using computers and software while at the same time, computer technology is even more important to them than others, because it helps them compensate for their disability. For instance, as I mentioned, my speech is significantly impaired, but I can use software technology to communicate. With that said, there are nearly as many variations on requirements for adaptive software as there are people who use it. As you can see in the video, I can't use a mouse. I can't use a keyboard either. The good news is that people with impaired muscle control can use adaptive devices and software to overcome issues like this, to access computers. However, the trade-off is that the process of using these tools is typically very slow. I would show you a video of how I do email, using a program called the Grid 2, but we don't have that much time. The message here is that there is no one-size-fits-all solution. Our system must be tailorable to address the specific needs of each user. Our group is not the first to investigate and develop an application to fill this need. There are a number of programs on the market, but each has its strengths and weaknesses. Our overall system objective is to try to take the best aspects of each of the applications and to address the shortfalls we see. The bottom line is that we want to give users independence. We want them to be able to configure the application to meet their specific needs. When the computer boots, the application should be ready to go and remain dependable while it is being used. The user should be able to do anything anyone else can do with a computer. Whether they are using the application as a communication tool, doing work, surfing the web, or playing games, we want them to be able to do it as efficiently as possible. Finally, many of the existing applications come with a high price tag. We would like to create this as an open system available at low or no cost. To achieve the system objectives outlined in the previous slide, we envision a system with an efficient virtual keyboard and mouse control, that can be accessed using a switch, eye gaze system, or by touch. In order to facilitate typing and communications, it will have a word and sentence prediction capability, as well as a text-to-speech component. All of these components will be configurable for use with different hardware, typically USB devices, and to adapt to specific user needs. The use case diagram on this slide shows the components of the system including a user profile, the virtual mouse and keyboard, and the word and sentence prediction modules. The user profile, word prediction, and sentence prediction have an underlying database to facilitate these functions. While we are investigating using existing word and sentence prediction modules, it appears the user profile will be a custom module. The main takeaway from this slide is that the user will be able to translate their thoughts into action and meaning using these tools. Next, we want to talk more specifically about our approach to the system development. Lee will provide a project description and discuss some of the development details.
My name is Lee Trin. As Jonathan said, I will be talking about some of the other details of our project. Because of the complexity of the problem space, and the limited completion time for the project, we decided to limit the scope of the development portion of the project, to just address keyboard accessibility for people with motor and dexterity impairments. While we are limiting the scope of the project to this module, we are building it within a framework that will allow for implementation of the mouse control and user profile, as well as incorporation of word and sentence prediction capability in the future. We will discuss these aspects of the system as well. This slide shows the overall system class diagram with the components of the user profile outlined in red. As you can see, it is the central component that all other modules depend on to define the specific parameters that address the user's needs. The user ID is the key field for all classes. The General Settings class allows the user to define language, printers they will use, and system behavior on startup. The Screen Appearance class provides control of cell appearance as well as workspace colors and font. The Input Settings class defines the hardware the user will use to access the computer. The Speech Settings class allows the user to define feedback sounds, select and modulate a public and private voice, and adjust word pronunciation, and other speech output rules. The Dictionary class defines the specific dictionaries used for word and sentence prediction, and finally the Workspace Settings class allows the user to define settings for specific applications and hardware. The graphic on this slide focuses in on the other system components, including the mouse control, word prediction, and sentence prediction modules outlined in green. The virtual keyboard module, which is the primary focus of our current project, is outlined in red. As you will see in the demonstration, it is a fully functional keyboard. In future versions of the application, the user will be able to tailor keyboard templates to their needs. Next, we will address some of the specific project development details of the system, including a discussion on platforms, frameworks, and other considerations. Our user community uses desktop, laptop, or tablet computers, most with Windows operating system. Windows supports a wide range of USB devices, including the Switch and iGaze systems employed by our user community, as well as a native touchscreen capability. The choice of Windows operating system made .NET the likely candidate for our programming framework. We selected the C++ programming language for the application development, primarily because of our familiarity with it. We also looked at several integrated development environments for this effort. We decided on the Visual Studio IDE because team members were familiar with it. Visual Studio has a configuration management capability, but we decided to use the GitHub configuration management tool to coordinate our efforts. Finally, we will use SQL Server Express as the database to support our user profile, as well as word and sentence prediction capability in the future. From a security perspective, we considered a layered architecture, even though this is not a critical system with the need for authentication protection. This allows us to place our database on the bottom layer with the interface on the top. Regarding access, Jonathan identified an issue in his current system where the user account control initiates when installing a new program. A third party must click OK to accept the change. To address this installation issue, our program will create a shortcut through the task scheduler with high-level permissions. To address change and increased functionality, we will use patches, and develop our program with maintainability and refactoring in mind. We are also considering using plugins to add functionality, despite the risk of obsolete code from third-party developers. Another possible change approach is to have a regulated marketplace which will allow users to review apps and add their own. One of our key objectives is to ensure the reliability of our application. The more we test, the closer we come to this objective. This graphic shows a portion of our test plan. Essentially, it is showing that we test each key to ensure it is sending the right instructions to the controller, which in turn, will send the key entry to the current application. We want to wrap up our presentation with the demonstration of this capability by our team leader, Damian Castroviejo.
Hello, my name is Damian Castroviejo, and I'm going to do a demonstration of our keyword application. In this case, I have the application running here, and I also have a Visual Studio empty file here so we can type some examples. So I'm going to start typing public class. So as you can see, as I'm typing the letters, they are sent to the active window. I can also use the shift to type capital. I can do backspace in this case that I have a typo, so let's write again, class 1, and I can also use the caps for the parentheses. If I want to keep typing in capital letters, I can deactivate it. I can move to my right with the arrow, and I'm gonna type bracket, enter, and let's see, integer I space equals. It also supports key combinations like the Control A to select everything, Control O. So if I do Control A, it selects everything, and I could, for instance, delete the whole content. If I want to undo that, I can use the hotkey Control Z, and it gets back. One of the major problems or challenges that we found on this application was to identify the active window, so we can send the key values from the keyboard applications to the active window. So the way we solved that was creating a process that is constantly checking the active window, and it saves the previous active window. And the reason is because as soon as we press on the keyboard, that becomes the new active window. So that's why we need to save what was the previous window. So that's why when we press any letter here, it sends to the previous active window. And we can switch to another application. Let's say I have a notepad here. So now this is my active window, but as soon as I type here, it knows already which was the latest or the previous active window, and it works the same way as I did before. I can do combination of keys and use as a regular keyboard. So this is pretty much it. I hope you liked it. Thanks.
In summary, Damien, Lee, and I covered an overall description of the problem we are addressing, as well as a description of our target adaptive user interface system that we believe will take the best from existing systems and fill in the gaps in these systems. Lee talked about our specific project objectives and discussed some of the specific details of our approach to our project. Finally, Damien provided a demonstration of the virtual keyboard component of our application. This concludes our presentation. Thank you for your time.